Okay, so this is my problem solving journal number 6 for measurement. And one of the things that I wanted to explore a little bit more was this website here by Dan Meyer. I did a little bit of digging around about him a couple of semesters ago, and I'm trying to keep up with everything that he has going on. And one of the things that I really liked was this 3-act math. So he gave this really great TED Talk about pulling kids in and not giving them so much information to kind of spark that natural curiosity that they have in math and let them consider all of the different variables that go into play with a problem before giving them all of the information and asking them just to follow the algorithm to find the answer. So I came here to his 3-act math, and that basically is he sets up just a very minimal problem for the student, and then there's a lot of discussion about the information that they can gather and what they need to be able to solve the problem. And then in the 2nd act, he provides a little bit of more information, and then students go back and rethink, the information that they need and try to solve the problem or gather more information. And then the 3rd act is the answer. So I came here looking for an activity that I could do for measurement, and the very first one, just because it's so popular right now, was Pokemon Go. So here is the 1st act of the video. And we don't...
5 kilometers, that's way too far.
Let me see.
Yeah, that's just a trick to make you exercise. Watch this. And now wait.
Nice.
So that's the 1st act, and we don't Pokemon Go in the Vanden Bosch house, but I know it's very popular, and I thought that it was definitely an interesting problem. So after the video, the question is, how long will the fan have to spin until the 5 kilometers egg hatches? And this is the part where we would have to make some guesses. So a guess that I know is too high. Like 24 hours is absolutely too high. I guess I'm assuming that's supposed to be too low, like 10 seconds, way too low. What is a guess you think would be just right? 5 kilometers. So I guess part of the conversation would be how fast, like if we could measure how long it takes the fan to make one rotation, and what that distance is. So if we made a circle there on what the rotation was, then we could figure out the distance that the phone is traveling in one rotation and how long that is. And then, so I would need to know time of one rotation, and maybe the length, if I could get the length of one blade then that would give me the radius, and then I could figure out this circumference here, maybe for distance. So if I was doing this in the classroom, I think it's a great problem just to see what kids know about the information that they would need to solve that problem. If they're understanding the relationship between radius and circumference, if they understand rate, just all of that vocabulary that's going to go into measuring that distance. The next part, so Act 2, here it says, show the students the contrasting cases. So when we look at this, a few things that I'm noticing are the placement of the phone. So here on the left-hand side, we've got the phone placed on the outer part of the fan, and here we have the phone placed on the inner part of the fan, and it looks like the top two fans were traveling at the same speed, and the bottom two ones were traveling at the same speed as well. So those are some things to consider, because in our video up here, the phone is taped to the end of the blade, and is that going to make a difference? Then we get this video of, here he's got a timer, and then we can count how fast the fan. Okay, so if I'm using one full, let's see, I feel like I need somebody to help me with that part. So let's see, if I pause it and I put it right at a minute, and okay, it's right here. I'm going to try to see if I can pause it when it gets right back to the same spot. Maybe a little less. Okay, so I have 78 hundredths of a second. Let's see if we can get one more rotation. Okay, so I've taken a few measurements and I've kind of just built a very simple chart where I'm recording which rotation I am on and the time for it. And I don't know if you can see that, but the average, here's my chart. The average rotation is about 75 hundredths of a second. Okay, so I went ahead and recorded all the way through until the end, and which changed my average a little bit. It put me at around 8/10 of a second per rotation. So here on the teacher's note it says the length of the fan blade is 45 centimeters. So if I am looking at the fan blade being the radius of a rotation, then one full rotation will be 2 pi times 45 centimeters. And then I have one rotation is about 0.8 of a second. One rotation is also 2 pi times 45 centimeters. And then I'm just going to do some conversions here. I'm going to convert rotations into distance, which is in centimeters. And then I need to convert centimeters to kilometers, which if I were a student I would probably stop at meters first. So I would say 100 centimeters is 1 meter, and then 1 meter is 1,000 kilometers. 1 kilometer is 1,000 meters. And that, let me pull up my little calculator here. 2 times pi times 45 282.74. Okay, and then I am going, so right now I have 0.0035 kilometers per second, and I want to see how many seconds it takes to get to 5 kilometers. 35/10,000ths of a kilometer. So I'm going to that is going to give me 1,428.6 seconds. I'm sorry, I'm being really lazy right now. Okay, so (23 minutes and 48 seconds is what I'm guessing. So after that, okay, they've got student sample work here. Let's see. So this looks a little different than mine. They've got, okay, they went with 8 seconds instead of, I did one rotation per 8/10 of a second. And that's not too far off. 23 minutes and 34 seconds. Okay. And so his Act 3 is the answer. So I guess this is the little Pokemon. Oh, it's funny. So the phone was moving too fast and we got called a cheater. Okay, so after this, other people who have done this kind of come in and contribute either questions that you can go and look into, have students think about or investigate. And I think that's it. I really do like this setup of the 3-act question. I think that it has students students are in a situation where they're more critical thinkers, and the real life application of not being provided all the information that you need to solve a problem, and instead really having to think about what information that you have to gather is a lot more realistic math that students will encounter as adults.